So you want to really understand the magic behind successful machine learning algorithms, right? But then you look at the prerequisites, and yeah, it's a lot. It's a massive, intimidating wall of advanced math. Well, today we are going to demystify those essential mathematical building blocks. We're going to build a bridge right over the gap between high school math and the advanced foundations you actually need to build modern algorithms. You know that feeling when you open an ML paper and it's just a wall of Greek letters? Total panic. As Steven Strogatz famously noted, people treat math like we're discussing spiders. If looking at machine learning literature gives you a sudden spike of anxiety, you are absolutely not alone. Even seasoned developers get overwhelmed. But today, we're conquering that fear brick by focusing only on the core concepts you actually need. Okay, here is our roadmap for today. We'll cover the machine learning math gap, linear algebra, geometry, decompositions, probability, and finally, the foundation for learning. Let's dive in. Section 1. The machine learning math gap. From phobia to foundation. To actually build this bridge, we need to know exactly where we're going. Machine learning fundamentally boils down to 3 core pillars. First, data, which is just taking real-world objects and turning them into numbers. Second, the model, a simplified, bite-sized version of reality. And third, learning, the process of automatically extracting valuable info to predict outcomes. Every single scary math term we're going to look at today is just a specific tool designed to support one of these 3 things. So that brings up an obvious question. Once we have all this raw, messy information from the real world, how do we actually organize it in a way that a computer can digest? That takes us to Section 2, Linear Algebra, organizing data through the rules of vectors. This first tool is all about structure. Linear algebra is fundamentally how we represent data in machine learning. Notice how we use linear mappings to take intuitive concepts and formalize them into strict rules a computer can play with. By setting up these vector spaces, it's kind of like creating a digital playground where data can be transformed, combined, and moved around systematically. It's the ultimate organizational system. Vectors really are the ultimate containers for our data, but people definitely look at them differently. Ask a computer scientist, and a vector is just an array of numbers. Ask a physicist, and it's an arrow pointing somewhere with a specific magnitude. But in mathematics, which is the engine powering our machine learning, a vector is simply an object that obeys 2 golden rules: addition and scaling. Master that concept, and you've mastered the language of your data. Okay, so our data is perfectly organized into these neat little vectors. But how do we measure the similarities between them? If our algorithm is going to predict that similar objects have similar outputs, we absolutely need a mathematical way to define what similar actually means. Which brings us to Section 3, Geometry, measuring similarity using distances and angles. Analytic geometry is basically our ruler and protractor here. Visualizing lengths and angles shows us exactly how to project high-dimensional data down to something we can actually manage. Just imagine taking a highly complex 3D object and casting its shadow onto a flat piece of paper. That orthogonal projection is absolutely crucial for simplifying data while keeping the core relationships totally intact. To pull this off, we rely on analytic geometry. By constructing inner products, norms, and metrics, we give our models a concrete mathematical way to understand distance. This is literally how a model figures out that an image of a cat is closer to another image of a cat than, say, a picture of a bicycle. And this geometric logic scales beautifully. We can even take complex, continuous functions like sine and cosine and compare them geometrically to see if they overlap at all. Here, the inner product evaluates to exactly 0, which proves they are completely distinct, or orthogonal. We use that exact same logic to isolate unique, non-overlapping features in our data. But here's a huge practical problem. What if we have gigantic matrices of data? I'm talking millions of rows and columns. How do we compress them to find the most important hidden features without literally melting our computers? Dealing with huge data sets requires our next powerful tool. Section 4, Decompositions, finding hidden patterns by compressing the matrices. Matrix decomposition lets us break down incredibly complex data tables into their fundamental, easy-to-read parts. Check out singular value decomposition, or SVD, in action. From a totally random-looking matrix of user ratings, the math automatically extracts hidden categories, like a science fiction theme or a French art house theme. It groups similar users together, boiling a massive table down to a few powerful characteristics. This isn't just abstract theory, it's a massive computational cheat code. Decomposition extracts meaningful info, drastically reduces memory usage, gracefully handles missing values, and acts as powerful data compression. Honestly, it's the secret sauce behind pretty much every recommendation engine you've ever interacted with. But as we all know, the real world is rarely perfectly organized. Our data is usually messy. So how do we handle the inevitable noise and uncertainty? To separate the true signal from the noise, we've got to learn a new language. Section 5. Probability. Modeling uncertainty using the language of noise. Probability gives us a principled foundation for quantifying uncertainty in literally any real-world problem. And there's a really important distinction here. Probability is modeling an uncertain process to figure out what might happen. Statistics is looking at what already happened to figure out the underlying process. Machine learning sits right at the intersection of the two, using probability rules to find the absolute best statistical model for what we observe. Now, ML literature is unfortunately packed with confusing probability jargon, so let's cut through the noise. The sample space is simply all possible outcomes. The target space covers the specific states we actually care about. Discrete variables are just categories, while continuous variables represent flowing numerical landscapes. Once you get this basic nomenclature down, you won't get hopelessly lost in the weeds. Section 6. The foundation for learning, bringing it all together. So we've built the pillars, we organized data with linear algebra, measured it with geometry, compressed it with decompositions, and handled the noise with probability. We made it across the bridge. Mastering these foundational tools, like partial derivatives and gradients, is what actually empowers you to build complex systems like density estimators and dimensionality reducers. You can clearly see how the core math feeds directly into the applied machine learning algorithms. You now have the mathematical blueprints. The gap between basic math and advanced machine learning isn't some terrifying void anymore. It's a bridge constructed of linear algebra, geometry, decompositions, and probability. You've got the tools, and hopefully the anxiety is gone. So the only question left is go out there and start building incredible things. What real-world magic will you choose to engineer?